Hello everyone. So I welcome you again in my lecture, and today we are going to talk about Quicksort analysis. So first we will see that what is Quicksort algorithm, and then we will analyze the algorithm to check its performance. Then we will also try to find out the best and worst case scenarios to identify the performance of this algorithm on different set of inputs. Okay, so let's start. So one thing to keep in mind that the design technique that we are using in the Quicksort is divide and conquer. We already discussed about the divide and conquer in our previous videos. Now we'll see that how the divide and conquer approach is applied in the Quicksort. So this is the pseudocode for Quicksort, and here you can see it is a very simple logic, and the entire pseudocode is defined in 4 steps. So Quicksort is a name given to this logic or this algorithm. Here we are passing 3 parameters. A represent the array on which we are working on. P is the first index of the array, and R represent the last index. So when we start working on this algorithm, you need to pass the array on which you want to work on, the first index and the last index. And we apply some logic until the first index, the value of P is less than the last index, the value of R. Here we are using one method that is called partition. So partition is basically the heart of this algorithm. So the main job is done by the partition. So in order to understand the Quicksort algorithm, we need to understand what is partition. Partition is basically an approach where we are dividing our bigger size into smaller subproblems. As we know that Quicksort is a divide and conquer based strategy. So we need to divide our array or a sequence of element into smaller size arrays. That we are doing with the help of partition. Now some points to note here that partition is going to perform on the given array, and in return it will give you one integer value. This integer value represents the index of the array. This determines that from which index, at which index we are going to make partitions. So if the q is the partition index, that means we have one part this side which is from the first to q minus 1, and we have one this side which is q plus 1 to the last element, to the last index. So we apply the partition, we get this q value. On the basis of q, we are going to make two sub arrays, and then again we keep on applying the procedure to all these sub arrays, or you can say to these sub problems. So here you can see that we call the partition. In the partition we are passing our array, the first index and the last index, and on the basis of q we are going to make two arrays, and then the two arrays will become individual problem that we are again calling it by the recursive calls, which works on both the sides. So here you can see that we have one part for which we are making this Quicksort. We are passing the array, the first index will be this, the last index is the q minus 1, and in the other part we again calling, we are passing the array, we are passing the first index. Now the first index becomes the q plus 1, and the last index remains r. So it's keep on working until you meet to the exit condition. Okay, so let us take an example. This is example where we have 1 2 3 4 5 6 7 element need to be called. So you make a call Quicksort, you pass this array a, let's say this is an array a. You need to pass the first index. So first index, if you are working with an array in the programming language, so first index is 0, so you will just make it here 0. Actually here I am writing the first element. Okay, so when we work with the arrays, so you have to pass the first index and the last index. So in this case this will be 6. So we pass A06. This is 0, 1, 2, 3, 4, 5, 6. So you have to pass this index. Now we are passing the index, we are not passing the value. So when you make a call, you are calling like this A06. We are not calling like this A and the value at this index 5 and 4. This is wrong. We are only passing the indexes, not the values. This is indexes. and these are the values at this index. So this is a wrong representation. We are passing this.
So let's discuss how the partition works. This is the main method of the quicksort, which takes three parameters: the array, the first index, and the last index. The objective of this partition method is to divide the entire sequence into two parts, and the basis of division is a pivot element. So here we take one pivot element. The pivot element can be any element, but in general practice we assume the pivot element as the first element or the last element. So in this example I am going to explain you by considering the last element as a pivot element, and our objective in this algorithm is to place the pivot element in its proper position. So we place the pivot element in such a way so that the left hand side of the pivot is less than the pivot element, and the right side of the pivot is a is more than the pivot element. What does it mean? It means if I have element 1, 3, or you can say 11, 3, 7, 8, 12, let's say 6. Now if I apply the partition on this, then this will be my pivot element, and the objective of this partition is to place the pivot element in the correct position. So what is the result after running these steps? We will get the pivot element placed at proper position in such a way so that on the left hand side we will get the element which is less than the 6, which is less than the pivot element, and the right hand side we get the element which is more than the pivot element. Now keep in mind, the only thing that we observe here is that these elements are more and these elements are less than the pivot, but this itself is not sorted. What is sure? This is all more than 6, but this is not sorted. What is sure? This is all less than 6 but not sorted. Now this becomes a new problem for us. This is a new sub array which we have derived from this initial array, and then again we have to apply this partition, and we keep on doing until we reach to the array of size 1. So how to perform this we will see. So let's work with an example. Let's say we have an array with the values 6, 6, 8, 7, 2, 4, 3, 5. Let's say these values are given to us, and then we are going to make a quicksort. So in the quicksort we need to pass this array. So we will pass the array. We will pass the first index, that is, here we can say this is 0, and the last index. So here you can see this is array. This is 1, 0, 1, 2, 3, 4, 5, 6, and the last index. And then you have to call the quicksort. When you call this method, the very first step is you need to call the partition. So here we will see that how the partition will work. So partition is called, we pass the array and we pass 0 and 6. Here we will assume the last element as the pivot element. So the last element is this one. So this a of 6, the a of 6, I am calling this array as with the name a. So a of 6 is 5. So here we store the value 5. Now this becomes the pivot element, and our objective is to place this element in the correct position so that the left hand side will be less than 5 and the right hand side will be more than 5. This is what we are trying to do in the partition. So here we will take some variables to perform this task. So I will be p minus 1. P is the first index. So keep in mind that here we have the first index is 0. So I will be minus 1, which is just left to the value of p, and j will go from p to r minus 1. So we have to make a loop from the first index to the second last index. This is the range of j, and j will be, and I will be initially p minus 1. So initially when you start, j is equals to 0 and I is equals to minus 1. So now let's see how the entire logic will work. Okay, so j equals to p. So initially we have j equals to 0 and I equals to -1. If a of j is less than x, now what is x? X is this value, which is 5. So a of j, if this value is less than x, then we need to increment the I value, the value of I. So because this is not true, this value is not less than this, so I will remain here, and you will go to the next value of j. Now j becomes 1. Now if this value is more than, if a of j is less than the pivot, now this value is not less than pivot, so again we are not going to change the value of I will remain -1, and you move to the next iteration of j. So now it becomes 2. Again you will compare. If this 7 is less than 5, no, it is not less than 5, so again you simply go back, and now j becomes 3. I is still -1 here. Now you are here, j is here now. Now you compare. If a of j is less than equals to x, now is this value less than this pivot value? Yes. So when this condition is true, you need to move to the this part. So increase the index of I, so I becomes now 0. And then what you are doing, you are going to exchange ai with aj. That means what is aj? Now this is j index and this is I index. Now you are going to swap this and this. So what you will get? You will get 2, 8, 7, 6, 4, 3, 5. And what is j? J is 3, and what is I? I is 0. Okay, so now you go to the next iteration. Now this becomes 4, and now you will check, is a of j, means if this value is less than 5, yes, this is less than 5. What is required? You need to increment the value of I is going to be increment, and then you have to swap the value of I and j, means you have to swap the value of a of I with a of j. You need to swap, so you have to swap these two values. So what is at this position? This is 4, and what is the position at I? 8. So you have to swap this and this, these two. So you will get 2, 4, 7, 6, 8, 3, 5. Now what is required here? Now j is equals to 5. Now j will go to the next iteration, it becomes 5, and I is 1. Now when j moves to the 5, that is the last index for this iteration. This is the last value, because it has to go up to r minus 1. So it will check, is this less than the pivot value? Yes. Then what is required? You increment the value of I, and then swap these two indexes. So you have to swap with the 5th index and the 2nd index. These two you have to swap. So what you will get? You will get 2, 4, 3, 6, 8, 7, 5. Now your for loop is completed, and then you will move to exchange. Now what we are doing? We are incrementing the value of I. So what is I? I is 2. So now I becomes 3. So you can write the index as well here, 0, 1, 2, 3, 4, 5, 6. So now I is pointing to this index, and you have to swap the value of a of I plus 1. That is, now I is actually 2 here, so I plus 1 is this. So this is I, and this is what? I plus 1. So what you get? This index, and this you have to swap with this last index. So what you get? You get 2, 4, 3, 5, 8, 7, 6, and this is the end of the algorithm, and you are returning I plus 1, means you are returning this index, which is 3. Now what is the observation here? When we perform the entire partition algorithm, we are able to find this 5th this element 5, which is our pivot element, in its correct position. Now if you look, this side is all less than 5, and this side is all more than 5, though it is not sorted, but we are able to uh, partition in such a way that the left hand side is less than 5, right hand side more than 5. That means 5 is now at the correct position, and it returns this index 3. So we have already seen that when the partition is called, partition returns one index, and that index is basically the dividing factor, means from which index we need to partition. So now again we have to call the quicksort. So we need to call the quicksort two times. One quicksort we are calling for the left array that we get, and the right and the one quicksort we are calling for the right array. Okay, so let us move further. Also, what you observed here, we have observed here that the very first time when the partition is called, it returns the index 3. So let us note these things. So far, when we call first time, the q with the value of q is what? 3. It returns 3. And so far what we get? We get 2, 4, 3, 5, 8, 7, 6. Now we have to work on this array and this array. So initially we started with this. Is, if you take this as an entire one problem, then this actually is the P and this is R. But now when we have did the partition, now we have to do from P to Q minus 1, because this is the index Q, from, and this is Q plus 1 to R. This is now the new array which we got, and we have to work on this. So here, what is P? P is again the index 0, and what is Q minus 1? Q is 3, so we get 2. So now we have to work from 0 to 2, and we have to work from 4 to 6. This is what we were having. Now if we look at this, so again when you make a quicksort call, then it will call a partition, and again partition will take the array. This is array. It will take the first index and the last index, and now you have to work on this 2, 4, 3, and this will be treated as a pivot element. Okay, so now here P equals to 0, I equals to minus 1, and your X equals to 3, which is a pivot element. So here we are again doing this partition operation. We did this thing, we did this thing. Now J has to go from P to R minus 1, so we have to make a loop 2 times only, from here to here. If A of J, if means if this value is less than equals to this, then increment I. Yes, this value is less than this, so what we have to do is we have to increment I. So what is I? This is your I equals to minus 1. We increment the I, so I becomes 0, and then we have to exchange A of I with A of J. So what is J? J is actually 0. When I say P equal to 0, that means the initial value of P is given to J, so J is 0. So I can write this as a J, because we are doing the loop in terms of say, so J equal to 0, I equal to 0, and we need to exchange the two values. So since the index is the same thing, this is 0 index, so nothing is going to change. This value is actually swapped with itself, so nothing is going to change. And now the value of J is going to increase, so now J is 1. So earlier the J is this, now J is this is J, and I is actually here 0 only, this is I. So now what is happening? Again you are doing the same thing. You are checking, is this value less than this value? No, this is not true. So you will simply skip this part, and then you go to next iteration, and you will find that your for loop is finished, because for loop has to go up to this point. You will come out of the for loop, and then you have to increment the value of I. So what is I? I is 0. You increment the value of I, it becomes 1, and you have to swap with the pivot element. So Now you have to swap this from here. That means what you get 2, 3 and 4. Now what is the observation? Now our partition is finished, and what we get we are able to keep this element in the correct position, because you can find the left hand side is is less than 3 and the right hand side is more than 3, and this index is 1. So this partition is going to return index 1, means at this position we are going to divide. Now we have two arrays. This is the left array and this is the right array. So when we reach to the situation when your array consists of only one element, then you are not going to call it again. You are not going to make a recursive call, because if you remember in the quicksort algorithm we are doing this task when p is less than r, means the first index must be less than r. Now in this case this is the only element, so this is the first index, this is the last index, so there is no need to call and we will stop. That means we are able to sort the left hand side array. So now so far we get 2, 3, 4 and 5. This is already there. Now we have to work on the right hand side. So let us see how the right hand side will work. So let me write it here. 8, 7, 6. This is my j. Now j is what? J is position number 4. And what is I? I is j minus 1, so I is 3. And what is x? X is my pivot element, which is 6. So I need to make a loop which goes from the first element to the second last element, means up to here. Okay, now so I did this step. I find my pivot, which is this. I did the initialization of I, so I is 3 here, and j will go from the first element to the second last element. Now I will check if this value is less than this. No, this value is not less than equal to 6. Then this condition is false and we go to the next iteration. Keep in mind that this is only going to execute when your condition is true. When condition is not true, then we will simply skip this part. So I is not going to increase. I will be remaining 3, and j will be increased because we go to next iteration. J will be here. Now we will see again, is this value less than equals to 6? No, that means this condition is false. We again go back to the next iteration of j, and you will find that the j loop is finished because j has to go up to this point. So you come out of the for loop, and here you will increment the value of I. So I will be now index 4. So I is pointing to this index and pivot is this index. You have to swap with the with this this ith index with the pivot element. What you get? You get 6, 7, 8. Now what is the observation here? Now this is your pivot element. You will find you are able to divide in such a way so that pivot element will make a division such that right hand side will be the more than pivot and left hand side will be less than pivot. So in this case 6 will be placed here, where the left hand side we find no element, but right hand side we find 2 elements. That means still we need to call again. So we will again make a call of quicksort, but what we will get here, what is the index of I? So it will index of I is 4, so we will get 4 here. So now keep in mind that these values are returned when you make a partition. So the first time you get return this index, what is this? 3. So you get return 3, then you get return 1, then you get return 4. Now this is our new array. We have to work on this. So left hand side there is nothing, right hand side is this. So now we have to work with the index 5 and 6. Okay, so how it will work? Our pivot element, this becomes a pivot element, the last element is a pivot element, and j will be going from 5 to 5 only, because we have only one element, because j will go from the first element to second last element. So there we have 2 elements, that means j will only iterate for one value, which is j equals to 5, and I is less than j, so I will be 4. Now we will check, is this element less than the pivot element? Yes, if this element is less than pivot element, then you have to increment I. So this is actually the position of j, this is the position of I, which is less than j. you have to increment I, and then you have to swap I and j. So I is 4. When you increment I by 1, it becomes 5. That means j and I points to the same position, so there is no need of any swapping. It will remain the same. Now your for loop finishes and you go out of the for loop, and you have to increment I. So I will be now 6, and then you have to swap this ith index with the pivot. Now you can see the pivot index and the new ith index is the same thing. That means there is no need to change, and the pivot value remains here. That means pivot is already at the correct position. This is only occurring when pivot is already at the correct position. So what you get this, that we are able to uh, divide into two parts. The right hand side is nothing, but the left hand side consists of only one element. So here we will return index 6, and now our entire array is sorted. So we have seen that how it is recursively calling every time. So if we make we see that how the call has been made. So you can just note down, just summarize all the things. So let me write it here. So here this is index 3, and then when the partition is being called, then we got this index 1, and here when it is being called, we got the index 4, and then we make a call for this, and there we get index 6. These are the index that we get when we call recursively Quicksort, and Quicksort in return call the partition. This is how we get it. So here you can realize when the Quicksort is called. So let us now trace that how these call has been made. So just keep in mind that we have the algorithm something like this. I hope you're remembering. This is a Quicksort. We pass A, P, R, first element, the last element, and here we will check the condition. If P is less than R, then we call the partition with A, P and R, and then after partition we again make a Quicksort call, Quicksort with A, P, Q minus 1, and we make a Quicksort A, Q plus 1, R. And what is this Q? Q is the value that we are getting after this partition. So based on this value of Q, based on this index, we are making the further Quicksort. This is how the algorithm is working. So let us now trace this. Let us make a kind of graphical representation that how the things are working. So here you can see that we have called the Quicksort, and I passed the array A, and I passed the index, first index, this is 0, last index is 6, and then in return, because this P is less than R, because the first index is less than R, it is going to make a call. So how it will make a part, it will call a partition. I am calling as a P, and it will pass array A, first index. So every time we need to pass an array, so I am just removing this part A. This is like understood. So we will pass the first index and the last index, and this in return call means when you make a partition, it will give you the Q value. So the Q value we are getting here is 3. So here we will make another Quicksort call, which is you are passing the array A, and you are passing the first index and the Q minus 1, which is 2. And also you are going to make a call Quicksort based on this partition. So you will going to pass the Q plus 1. Q plus 1 is what? 4, and the last index 6. So the very first call will do this job. You will call partition. Partition will give you the Q. Based on Q, you are again calling Quicksort. for the left hand array and the right hand array. Now this will again recursively call the quicksort. So what we will get, we will again use the partition. We have to pass the first index and the last index, and based on this, so this is this scenario that when we are working on this. So what we get, actually when you work on this, what we get the q value equals to 1. So based on this 1, it will make a quicksort. We will pass the first index, which is 0, and the last index q minus 1. So q is 1, so we will get 0 0. That means now we get only one element and there is no need to move further. It will stop here. And similarly, you will get here, you will call here quicksort, and you will call q plus 1. Q plus 1 is 2, and the last element 2 2. So now this will not go further, this will not go further. You will stop here. Now we are working on the right hand partition. So here when we start with the array, we have two partitions, the left side and the right side. We already worked on the left side. Now we see how the right side will be solved. So now I am calling this side. So here when you make a partition call, so you will pass this 4 6, and what is returned? So when you call the 4 6, it will return 4. So that means you have a quicksort here, and in the quicksort you will write the first element and the q minus 1. So q minus 1 is 3. Now quicksort is only going to execute when p is less than r. So here p is not less than r, the first index is not less than the last index, so it is not going to proceed further. And there is actually, the meaning of this is there is no left side array, means we are not going to get any left hand side partition, we are only going to get the right hand side partition. So we will see what is the status of right hand side. So quicksort, so here we get 4 is the index, we get q plus 1 to r, so 5 and 6. So here still the p is less than r, the first index is less than r, so still we are going to make a next quicksort call. So again it is going to call, we call partition, we will pass 5 6, and what you will get here, so when you call this 5 6, you are getting here 6. Already we have solved. Now based on this value 6, now based on this partition index, we need to see what is the further call made for the quicksort. So when you call quicksort, you will call from 5 to q minus 1, which is 5. That means now this is the only one element left and there is no need to make a further call. On the right hand side, when you make a call, you will find it will be q plus 1. Q plus 1 is what? 7 and r. So again you will find that p is more than r, so that means this is not possible scenario and we have to stop here. Now all the calls have been made, and if you find, already we have seen in our example that this will already give you a sorted list. Now let's see that how to compute this running time. Already we have seen that how this algorithm is working, how the partition is happening. Now we will see about its analysis. Let's move to next. So the performance of quicksort can be analyzed based on the partition nature, means how the partition has been done in the given array. So if it is balanced, when I say balanced means when you are dividing the array into two parts, then both the parts are of almost the same size, then it is said to be balanced. Now if you are getting a balanced partition, then the running time will be better and it is asymptotically equal to the merge sort. It is as fast as a merge sort. But if it is not balanced, means when you are doing a partition and you are getting one part is very small compared to the other part, then it is said to be unbalanced, and this is very much equivalent to the insertion sort algorithm. So in order to get your performance better, if your pivot element is chosen in such a way that it will divide your array into a balanced form, then you will be getting a better running time. So let's move. So let's take an example. Worst case, as I told you, that it is if it is unbalanced, and the most worst scenario is when you are dividing your array into two parts in such a way that the one part is actually consists of n minus 1 element and the other part consists of 0 element. And this is a scenario when you are having an array which is already sorted. So let us see that how it will happen. So the scenario is we have, let's say, array something like this, uh, 12, 19, 37, 82. Now what will happen if I apply the Quicksort, and when we do the partition, what I will do, I will assume this as the pivot element and I will run the pivot that partition algorithm. So as a result, what I will get, I will be able to place this pivot element at the correct position, and I will divide the array into two parts in such a way the left hand side will be less than 82 and the right hand side will be more than 82. So when you run your partition algorithm, what you will get, this is already in the correct position. You will find this is your one array, and the other side you will get an array of size 0. That means you get array 1 of n minus 1 size and other array is of 0 size. Now if this is the partition nature, means if you are doing a partition in such a way, then this is said to be a worst scenario. So how to represent this kind of scenario? We have a problem of size n, and then we are able to divide the problem into tn minus 1 size. So we have divided so that one problem will be of n minus 1 size and other will be of 0 size, and we did this by doing this n effort. Actually this is the cost of the partition method. So we apply the partition algorithm, and with the help of partition algorithm we are able to divide our problem into two parts, one of size n minus 1, other is of size 0. So we have this recurrence relation, that is t of n equals to t of n minus 1 equals to theta n, and you can see that with the help of Master's theorem it is coming out to be theta of n square, which is the same running time like the insertion sort. But one thing to keep in mind, that insertion sort is performing the best when you are providing the sorted array, but in the case of Quicksort, when the array is sorted, it will perform the worst, it will give you the worst performance. So you need to keep in mind all these scenarios, that the best scenario of insertion sort is actually the worst scenario of Quicksort. Now we will see the another scenario, that is the best case scenario. Now best case scenario, as I told you, that is a scenario when your partition dividing your array into two equal halves. So let's say you have a sequence something like this, 9, 13, 21, 86, 15. Now this is your pivot element. When you apply the partition, then you will do all the logic, and what you will get, 15 should be come in between, and you will get this side 9 and 13, and this side you get 21 and 86. I just doing it roughly because 15 will be in the correct position, and what we have observed, that the left hand side is less than the 15 and right hand side is more than 15, and the size of the left and right is almost same. So when I say best case, if your partition dividing the array into two halves of same size, then that becomes the best scenario. So in that case, you can say that you start with your size n, you did some amount of work, that means you would apply some partition method, that this is the cost of partition, and you are able to reduce your problem into two equal halves. So this is 2t n by 2, and if you apply the Master's theorem or any other method like recursive tree method or the back substitution method, you will find the running time of this recurrence relation is n log n. Now this is much better than the n square. So the conclusion is, when the partition is dividing into two equal halves or almost equal halves, we have n log n, and if it is dividing into like 0 and n minus 1, this becomes the worst scenario, and in that case it is big O of n square. So let us summarize here the overall scenario. Let us make two columns, one for the best case and other is for the worst case. So let's say this is your best case, then we have worst case. Now we will see, let's say we are representing this with T of n, then the cost of partition is big O of n. We will analyze this cost later. This is effort is big O of n. So here you can see that whenever you apply partition, it is the effort is big O of n. So either you are calling in best case or worst case, the cost is big O of n only. But when we say best scenario means you are able to divide your input size into two equal halves. So that means when you make this Quicksort is will be called with size n by 2, and this also will be called by size n by 2 in the case of best scenario. But when we talk of worst case, you are calling the Quicksort in such a way that one will be t n minus 1 and other will be t of 0. So this will be t of n minus 1 and other will be t of 0. So if we represent best scenario, we will get t of n is equals to t of n by 2 plus theta n, which is nothing but n log n. Similarly, when we write for the worst scenario, we will get t of n equals to t n minus 1 plus theta n, and if you solve this using Master theorem, you will get big O of n square. So this is all about the Quicksort algorithm, and we did this analysis. We identified that the Quicksort running time is n log n. In the best case, even we will see later that actually it is n log n in all the scenarios except the worst case scenario. In the worst case scenario, where we are dividing it into n minus 1 size and 0 size, then only it will be n square. So we'll take some more examples. There we will analyze that the running time of Quicksort will be actually n log n. So this is all for this lecture. We will be going to talk more about Quicksort in the next lecture. So thank you very much. Take care.